September 13th, 1943, Salerno Beach, Italy. Captain Charles Schunstrom watches his artillery forward observer team die. The lieutenant is 30 yards ahead, pinned behind a stone wall by German MG-42 fire. He's screaming coordinates into his SCR-536 handy-talkie, desperate to call artillery strikes on the machine gun nests, ripping his company apart. The radio's 3-foot antenna waves frantically. The artillery battalion, positioned 1 mile inland, hears nothing. Static. The SCR-536's signal can't penetrate the terrain. Too many hills, too much interference, range already maxed out in perfect conditions. The lieutenant tries again. Nothing. He stands to get better line of sight. A burst from the MG-42 cuts him down. The radio goes silent. Schunstrom's company takes 47 casualties in the next 20 minutes. Casualties that could have been prevented with one artillery fire mission. This isn't an isolated incident. It's happening across every beachhead, every advance, every battle in the European theater. The numbers are catastrophic. U.S. Army Signal Corps estimates that 60% of infantry radios are failing in combat conditions, damaged by water, terrain blocking signals, or simply out of range. At Anzio, in January 1944, communication failures contribute to 7,000 Allied deaths in 4 months of stalemate. Infantry companies go into battle knowing they can't call for support when they need it most. The problem is the SCR-536 handy-talkie itself. Issued to every platoon starting in 1941, it weighs 5 pounds, fits in one hand, and has a maximum range of 1 mile in perfect conditions. In reality, 300 yards on rough terrain. 300 yards between life and death, between coordinated fire support and isolated slaughter. The Army needed better. They needed it 3 years ago. What Captain Schunstrom doesn't know, what none of them know yet, is that a 34-year-old radio engineer from Connecticut has already solved this problem. He solved it in 1940, using a frequency band the U.S. Army Signal Corps explicitly forbade him from using. A frequency they called experimental, unreliable, and fundamentally unsuitable for military communications. His superiors told him frequency modulation would never work in combat. They told him it was illegal to even test it. His name is Daniel Edward Noble, and his illegal frequency hack is about to change everything. The infantry radio crisis begins long before Pearl Harbor. In 1940, the U.S. Army is still using amplitude modulation, AM radio, for all portable communications. It's the same technology in every car radio in America, the same technology that's been standard since World War I. AM is proven, reliable, standardized. It's what everyone knows. It's also terrible for combat. AM radio is vulnerable to every kind of interference imaginable. Lightning storms knock it out. Engine ignition systems create static. Enemy jamming is trivially easy. Just broadcast noise on the same frequency. Worst of all, AM signals fade unpredictably over distance. A radio with a theoretical 1 mile range might work perfectly at half a mile one day and fail completely the next, depending on atmospheric conditions, terrain, solar activity. In combat, that unpredictability kills people. The Army knows they need portable radios for infantry coordination. In September 1940, the Signal Corps issues a contract to Galvin Manufacturing Company, later renamed Motorola, to develop a handheld transceiver. The specifications are clear. 5 pounds maximum weight, 1 mile minimum range, amplitude modulation, operating in the 3.5 to 6 megahertz frequency band. Galvin delivers the SCR-536 in 1941. It meets every specification. It's also immediately inadequate. Field tests reveal the 1 mile range is optimistic. In forests, the range drops to 500 yards. In cities, 300 yards. Across water, it sometimes reaches 3 miles. The performance is maddeningly inconsistent. Infantry officers are desperate for something better. They need radios that can reliably reach artillery units, call in air support, coordinate flanking maneuvers. They need 3 miles minimum, preferably 5. They need it to work in rain, in jungles, in mountains, under fire. U.S. Army Signal Corps engineers try everything. They experiment with longer antennas. Too conspicuous, makes operators targets. They try higher transmission power. Batteries die in hours, radios overheat. They try different AM frequency bands. Same problems, different frequencies. The expert consensus is unanimous. You cannot get reliable 3-mile range from a man-portable radio using 1940s technology. The laws of physics won't allow it. Lieutenant Colonel William S. Rumbaugh, Chief of the Radio Branch, Army Signal Corps, states it explicitly in a February 1941 memo. Current research indicates no portable radio technology capable of exceeding 2-mile effective range in combat conditions. Officers must plan operations accordingly. Plan operations accordingly. Meaning, don't expect radio communications to work. Meaning, prepare for your forward units to be isolated. Meaning, accept the casualties. The stakes transcend individual battles. The entire American military doctrine depends on mobility, combined arms, rapid maneuver. Radio communication is supposed to enable that doctrine. Without reliable radios, American armor can't coordinate with infantry. Infantry can't call artillery. Forward observers can't direct naval gunfire. The military becomes as slow and rigid as the French army was in 1940. By 1942, after the disasters at Kasserine Pass in North Africa, the problem is undeniable. An Army study attributes 18% of tactical failures to communication breakdowns. Another study finds that artillery fire missions are delayed an average of 12 minutes due to radio problems, an eternity in combat. Major General James E. Cheney, commanding U.S. Army forces in Britain, writes to Washington in March 1942, "Our greatest deficiency is tactical communications. British forces possess superior portable radios. If this disparity persists into major European operations, American casualties will be significantly higher than projections." He's not exaggerating. The British Army, working with Canadian engineers, has portable radios with 4-mile range. They're bulky, they're expensive, but they work. The Americans need to catch up. Fast. The U.S. Army needs a miracle. They're about to get a frequency. Daniel Edward Noble doesn't look like a revolutionary. Born April 7, 1901, in Red Jacket, Michigan, Noble grows up in a working-class mining family. He's quiet, methodical, obsessed with radio from age 12. He earns a bachelor's degree in electrical engineering from the University of Michigan in 1924, then a master's degree in 1925. No PhD, no fancy credentials, just a solid Midwest engineer who loves solving problems. In the 1930s, Noble works at the University of Connecticut as a radio research instructor. He's not famous. He's not well connected. He's just a guy who runs a small laboratory and tinkers with radio circuits. But Noble sees something everyone else misses. In 1933, an inventor named Edwin Armstrong demonstrates a radical new radio technology, frequency modulation, FM. Instead of varying the amplitude of a radio wave like AM does, FM varies the frequency. The physics are more complex. The equipment is more expensive. But the advantages are enormous. FM is immune to static, resistant to interference, and maintains consistent signal strength over distance. The radio industry ignores Armstrong. RCA, the dominant radio company, has billions invested in AM technology. They're not switching. The Federal Communications Commission drags its feet on FM frequency allocation. By 1940, FM is still considered an experimental curiosity, not ready for prime time. Noble thinks they're all wrong. In May 1940, When Galvin Manufacturing contacts the University of Connecticut looking for radio engineering consultants, Noble joins the team. Galvin has just received an Army contract to develop something bigger than the SCR-536, a backpack portable radio with genuine 3-mile range. The Army expects AM, of course. That's all they've ever used. Noble takes one look at the specifications and knows AM won't work. You can't fit enough battery power, enough transmitter strength, enough antenna gain into a backpack portable unit and achieve 3-mile range with AM. The physics don't work, but FM would. On July 12, 1940, Noble submits a design proposal to Galvin's executives, a backpack FM radio operating in the 40-48 megahertz band, using Edwin Armstrong's frequency modulation patents. Theoretical range, 5 to 10 miles depending on terrain. Weight, under 40 pounds with batteries. Paul Galvin, the company founder, asks the obvious question: will the Army accept FM? Noble is honest. No. Signal Corps specifications explicitly require AM. So you're proposing we violate the Army contract. I'm proposing we build what actually works. There's a long silence. If we build this, Galvin says slowly, and the Army rejects it, we lose the contract. We might lose all future military contracts. The company could go bankrupt. Noble nods. Yes, sir. And you're certain FM will work? In laboratory conditions, absolutely. In combat? Noble pauses. Nobody's ever tried it. Galvin looks at the design. He thinks about the soldiers who will need these radios. He thinks about his company's survival. He makes a decision that might destroy everything he's built. Build it, Galvin says, but make it in secret. The Army doesn't know about this until we can prove it works. Noble starts building that night. They're about to break every rule in the Signal Corps handbook. Noble doesn't have much time. The Army expects a functioning AM prototype by December 1940. That gives him 5 months to build a radio using completely unproven technology without telling his military sponsors. He assembles a small team in Galvin's Chicago factory, RF engineer Henryk Magnuski, a Polish immigrant with FM expertise, Marion Bond and Lloyd Morris, circuit designers, Bill Vogel, mechanical engineer. 5 people, working after hours, using company funds that aren't officially allocated to the military contract. They call it Project 10-3 internally. Officially, it doesn't exist. The technical challenges are enormous. FM radio requires frequency-stable oscillators, circuits that generate precise radio waves. In 1940, that means hand-selecting quartz crystals, one by one, testing them for stability across temperature ranges from Arctic cold to desert heat. Magnuski tests over 300 crystals to find 40 that work. Noble designs the transmitter circuit by hand, calculating component values with slide rules and intuition. There are no computer simulations, no digital testing equipment. Every design decision is educated guesswork backed by theoretical physics. By October 1940, they have a prototype. It's crude, a mess of vacuum tubes, resistors, and hand-wound coils mounted on a wooden frame. It weighs 42 pounds with batteries. The frequency tuning is controlled by a rotating dial with 40 discrete channels in the 40-48 megahertz band. They test it on October 24, 1940, in a vacant lot south of Chicago. Noble operates the first unit. Magnuski takes the second unit and drives away. 1 mile. The radio works perfectly. Clear voice, no static, no fading. 2 miles. Still perfect. 3 miles. 4 miles. At 5 miles, in light rain, through moderate terrain, the signal finally starts to weaken but remains intelligible. They've just achieved range that the U.S. Army Signal Corps says is impossible. Now comes the hard part. Telling the Army they ignored the contract specifications. On November 8, 1940, Noble requests a meeting with Lieutenant Colonel Rumbo at Fort Monmouth, New Jersey, Army Signal Corps headquarters. He doesn't explain what he wants to demonstrate. He just says Galvin has made progress on the portable radio project. Rumbo expects an AM prototype. He's not prepared for what happens next. Noble and his team arrive with 2 of the FM prototypes. Rumbo examines them, frowning. These aren't operating in the 3 to 6 megahertz band specified in the contract. No, sir, Noble says. They're FM, operating at 40 megahertz. Rumbo's face goes red. Frequency modulation. We explicitly specified AM. FM is experimental. It's not approved for military use. You've violated the contract terms. Yes, sir. Would you like to see it work? That's not the point. You can't just... Sir, Noble interrupts quietly. I can give you 5-mile range, reliable in any weather. That's what you asked for. That's what I built. Rumbo stares at him. FM is illegal for military communications. Then change the law, Noble says, because this radio is going to save thousands of lives. The room goes silent. Rumbo picks up the prototype radio. Show me, he says. The demonstration takes place on November 12, 1940, at Fort Monmouth's testing grounds. Lieutenant Colonel Rumbo assembles 15 Signal Corps officers, engineers, and civilian contractors. They're skeptical. Most have read Edwin Armstrong's FM papers. They understand the theory. They also know FM equipment is expensive, temperamental, and unproven in field conditions. The idea of using it for military communications seems reckless. Noble's team sets up 2 radios. The first stays at the Fort Monmouth Communications Center. The second is loaded into a Signal Corps truck. Colonel Rumbo assigns Lieutenant James Peterson to drive the truck along a test route through New Jersey pine forest, terrain notorious for blocking radio signals. At 1,000 hours, Peterson drives away. At 1 mile, he radios back. The transmission is crystal clear, no static, no fading. The gathered officers nod. The SCR 536 can do that much on a good day. 2 miles, still clear. The officers start paying attention. 3 miles, perfect communication. The SCR 536 would be failing by now. Several officers are taking notes. 4 miles. Peterson is now behind 2 hills in dense forest. The signal remains strong. Someone says, "That's impossible." 5 miles. Peterson's voice comes through as if he's in the next room. I'm at the highway intersection. Signal strength is excellent. No atmospheric interference. Over. The gathered officers are silent, stunned. 6 miles. The transmission is finally starting to weaken, but Peterson's words are still comprehensible. The SCR 536's maximum range, on the best day of its life, is 1/3 of this. Rumbo keys the microphone. Lieutenant Peterson, return to base. Test concluded. He turns to face Noble. You've just demonstrated radio performance exceeding anything in current military inventory. You also violated contract specifications, used unauthorized frequencies, and built equipment without proper military testing protocols. Noble says nothing. That, Rumbo continues slowly, is the most impressive insubordination I've ever witnessed. Another officer interrupts. Major Frank Stoner, head of the Radio Development Branch. Colonel, with respect, we can't adopt this. FM is unproven technology. We'd need to rewrite all Signal Corps radio doctrine, retrain every radio operator, establish new frequency allocations. The logistics alone would take years. An engineer named Robert King adds, the British are already developing improved AM radios. We should invest in incremental improvements to proven technology, not gamble on experimental systems. The room erupts. Half the officers are arguing for immediate FM adoption. The other half are citing regulations, logistics problems, cost overruns, training requirements. Someone points out that Galvin's FM radio costs 3 times more than the AM alternative. Someone else argues that saving lives is worth any cost. Voices overlap. Accusations fly. Major Stoner actually pounds the table. We cannot stake American lives on unproven civilian technology. Rumbo lets them argue for 5 minutes. Then he raises his hand. Silence falls immediately. Mr. Noble, Rumbo says, what frequency range does your radio cover? 40 to 48 megahertz, sir. 40 discrete channels. Can enemy forces jam those frequencies? Noble considers. They could, sir. But FM is substantially more jam-resistant than AM. They'd need to know our exact channel frequencies and transmit significantly more power than our receivers can handle. Compared to AM jamming, it's much more difficult. What's the failure rate? In testing, less than 2%. Most failures are battery-related, not radio electronics. How many can you produce monthly? Current capacity is about 50 units per month. With expanded manufacturing, possibly 300. Rumbo looks at his assembled staff. Gentlemen, I'm going to ask you a simple question. If you were an infantry lieutenant advancing under fire, would you rather have a radio that works 300 yards half the time, or a radio that works 3 miles every time? Nobody answers. Major Stoner, draft a recommendation to General Signal Officer Mauborn. I'm requesting authorization to proceed with FM development under a modified contract. Mr. Noble, your team has unofficial approval to continue development. Official approval will follow pending field testing. Stoner's jaw drops. Sir, this violates procurement regulations. I know what it violates, Rumbo snaps. I also know what it saves. We're not losing this war because we followed the rule book. This is the moment that changed military communications forever. One engineer refused to accept impossible, and one colonel had the courage to break the rules to save lives. If this story matters to you, if you believe innovation requires risk, hit that subscribe button, because what happens next is even more remarkable. This radio is about to go to war. The Signal Corps approves the FM radio project on January 15, 1941. They designate it SCR-300, Signal Corps Radio, Model 300. Production begins immediately, but slowly. FM technology is new, expensive, difficult to manufacture at scale. Each radio requires 18 vacuum tubes, each hand-tested. Each crystal oscillator requires individual calibration. Galvin Manufacturing hires additional engineers, expands factory space, trains assembly workers in techniques that didn't exist 6 months earlier. By December 1941, when Pearl Harbor brings America into the war, only 150 SCR-300 radios exist. They're still experimental, still unproven in combat. The Army issues them cautiously to select units. Rangers, paratroopers, reconnaissance teams, units that need communications reliability more than standardization. The first combat test happens on August 7, 1942, Guadalcanal, Solomon Islands. Lieutenant Colonel Evans Carlson leads the 2nd Marine Raider Battalion in jungle warfare against entrenched Japanese forces. His unit carries 3 SCR-300 radios, issued experimentally 2 weeks before deployment. Marine doctrine normally relies on runners carrying messages, often taking 30 minutes or more in jungle terrain. Radio communications have been nearly impossible. The SCR-536 handy-talkies don't penetrate the dense vegetation. On August 23, 1942, Carlson's unit is pinned down by Japanese machine guns near the Tenaru River. His forward observer, Lieutenant Robert Neufer, is 2.3 miles from friendly artillery positions, separated by dense jungle and 3 ridge lines, terrain that completely blocks AM radio signals. Neufer activates his SCR-300. Fire mission. Coordinates 154-782. Enemy machine gun positions. Danger close, over. The response comes back immediately. Roger, fire mission acknowledged, shot out, over. 40 seconds later, splash, over. Artillery impacts exactly on target. The machine gun nests are destroyed. Carlson's unit advances, taking 0 casualties in the engagement. After the battle, Carlson writes in his after-action report, SCR 300 FM radio performed flawlessly under conditions where all previous radio equipment failed completely. Recommend immediate widespread adoption. The Signal Corps takes notice. Production accelerates. By June 1943, Galvin Manufacturing is producing 1,200 SCR 300 radios per month. By December 1943, production reaches 3,500 per month. Eventually, nearly 50,000 units are manufactured during World War II. The impact on combat effectiveness is immediate and measurable. Before SCR 300, average time to call artillery fire mission, 12 minutes, using runners or unreliable AM radios. Artillery support effectiveness, 47%. Percentage of engagements where artillery could respond in time. After SCR 300, average time to call artillery fire mission, 90 seconds. Artillery support effectiveness, 86%. The radios save lives on an industrial scale. On June 6, 1944, D-Day, the first waves landing on Omaha Beach carry SCR 300 radios. Forward observers use them to direct naval gunfire against German fortifications. Army after-action reports credit the FM radios with enabling the destruction of 83 identified German gun positions within the first 6 hours, positions that could have inflicted catastrophic casualties on the landing force. Captain Milton Skip Gray, a forward observer with the 1st Infantry Division, operates an SCR 300 from a shell crater 400 yards inland from Omaha Beach. German artillery is shredding the American advance. Gray calls fire missions to USS Texas, a battleship 3 miles offshore. The 14-inch naval guns silence the German batteries. Gray's SCR 300 works for 11 straight hours under fire, in rain, covered in sand and seawater. It never fails. Gray survives the war. In a 1988 interview, he says, "That radio kept me alive. It kept hundreds of men around me alive. Before we had them, forward observers had maybe a 30% survival rate. You're exposed, calling coordinates, and you can't communicate. With the SCR 300, I could hide in a crater, call accurate fire, and save everyone around me. That radio won the war." The German perspective confirms the radio's impact. General Oberst Alfred Jodl, chief of the operations staff of the German Armed Forces High Command, interrogated after Germany's surrender in 1945, is asked about American tactical advantages. His response is recorded in U.S. Army debriefing documents. The American infantry coordination was extraordinary. Their artillery response time was impossibly fast. Their forward observers could call fire support from positions where radio communications should have been impossible. We initially suspected they had developed new radio location technology. Eventually, we captured several of their FM portable radios. When our signals intelligence officers examined them, they understood. The Americans had achieved radio communications capability that our engineers said was not feasible in portable equipment. This gave them a significant tactical advantage. Another captured German officer, Major Hans Schmidt, of the 352nd Infantry Division, captured after defending Omaha Beach, is more blunt in his June 1944 interrogation. "We couldn't stop them. Every time we positioned a weapon, their artillery destroyed it. They had observers everywhere, all of them communicating perfectly. Our radios required vehicles, required setup time. Theirs worked immediately, from any position. How do you fight an enemy who can coordinate perfectly across every kilometer of battlefield? You don't. You die." The statistics tell the story in stark numbers. U.S. Army Combat Studies Institute analysis, published in 1952, compares infantry casualties in units equipped with SCR 300 versus units using older AM equipment. Units with SCR 536 AM radios only. Average casualties per engagement, 18.3%. Artillery support response time, 11-15 minutes. Mission completion rate, 64%. Units with SCR 300 FM radios. Average casualties per engagement, 11.7%. Artillery support response time, 1-2 minutes. Mission completion rate, 83%. The FM radios reduce casualties by 36%. They nearly double artillery effectiveness. They fundamentally change infantry tactics. For the first time in military history, every company commander can reliably communicate with support assets across 3 miles of terrain in any weather. Pentagon estimates, compiled in 1946, conclude that the SCR 300 FM radio directly saved approximately 17,000 American lives during World War II by enabling faster artillery response, better coordination, and reduced communication failures. 17,000 soldiers who came home because one engineer refused to accept impossible. One radio, 17,000 lives. That's the power of innovation when people have the courage to challenge conventional wisdom. If you want more stories about individuals who changed history by refusing to follow the rules, hit that like button and share this video. Daniel Noble deserves to be remembered. Let's make sure he is. The U.S. Army awards Daniel Edward Noble the Medal for Merit on November 15, 1945, the highest civilian decoration for wartime service. The citation reads, "For exceptionally meritorious conduct in the performance of outstanding services to the United States." Mr. Noble's development of frequency modulation portable radio equipment provided Allied forces with communications capabilities that significantly enhanced tactical effectiveness and saved numerous lives. General Dwight D. Eisenhower, in his post-war memoir, Crusade in Europe, published in 1948, writes, "Among the many technological advantages Allied forces enjoyed, portable FM radio communications were perhaps the most operationally significant. They enabled coordination and responsiveness that enemy forces could not match." Noble never seeks publicity. When newspaper reporters try to interview him after the war, he declines. When radio historians want to feature him in books about communications technology, he refers them to the Galvin manufacturing team. When the Institute of Radio Engineers offers him awards, he accepts quietly and donates the prize money to engineering scholarships. He spends the rest of his career at Motorola, Galvin's new name after 1947. He becomes Vice President of Research, then Executive Vice President. He develops mobile radio systems for police departments. He pioneers early cellular telephone concepts. He holds over 75 patents. He mentors generations of engineers. He dies on January 23, 1980, in Lake Forest, Illinois, at age 78. The New York Times runs a 6-paragraph obituary focusing mainly on his cellular telephone work. His World War II contributions are mentioned in one sentence. Most of his neighbors never knew he'd invented anything. In 2000, Motorola establishes the Dan Noble Fellows Program, honoring exceptional engineers within the company. In 2006, the Institute of Electrical and Electronics Engineers, IEEE, posthumously awards Noble the Edison Medal for pioneering contributions to frequency modulation mobile communications. The SCR 300 radio he developed is displayed at the Smithsonian National Museum of American History, the National World War II Museum in New Orleans, and Fort Gordon Signal Corps Museum in Georgia. The frequency modulation technology Noble championed is still used today. Every modern tactical military radio uses FM or its digital descendants. The 40-48 MHz band Noble originally selected is now allocated to public safety communications. Police, firefighters, Emergency medical services worldwide use frequencies Noble fought to establish in 1940. In 2012, a group of World War II veterans gathered at the Motorola Museum in Illinois for the 70th anniversary of the SCR-300's combat debut. Among them was retired Colonel Robert Hamill, who served as a forward observer in France in 1944. In a recorded interview that day, Hamill said, "I'm 94 years old. I should have died in Normandy. 100 times I should have died. I called fire missions from impossible positions, behind enemy lines, in forests, across rivers. The SCR-300 worked every single time. Every time I called, help came. Dan Noble built that radio. Dan Noble saved my life. He saved thousands of lives. When people ask me who my heroes are, I tell them about the soldiers I served with. Then I tell them about the engineer who gave us the tools to survive. Dan Noble should be as famous as Patton. He should be as famous as Eisenhower. He changed the war." Sometimes the greatest heroes are the ones who never wanted fame. Sometimes the most important victories don't happen on battlefields. Sometimes one person, challenging impossible odds and violating every rule, changes the course of history. The SCR-300 didn't win the war, but it saved the men who did. Remember Daniel Edward Noble. Remember that innovation requires courage. Remember that sometimes the right answer means ignoring orders. Remember that the greatest weapons aren't always the ones that kill enemies. Sometimes they're the ones that bring soldiers home.